Capers, you're very welcome, and we thank you very much for taking your time to hold this pro bono talk. So please, the floor is yours.
Thank you very much. It's a pleasure to be there. I always like visiting Sweden, and sorry that I'm not there actually with you, especially given the hurricanes and winter storms and other bad weather that we're having locally. But in any case, here we are connected. My talk today is on achieving excellence in software engineering, and it's derived from studies in over 150 large companies, total collection of about 13,000 projects gathered over the years. Because we have 30 minutes, I'm going to skip quickly through some of the slides that only list information, and then concentrate on the slides that actually have some significance to CMAT and to making improvements in software engineering technologies. So with that, I'm going to jump into the first slide, which shows kind of a history of significant software innovations. And there's more than one slide of innovations. And it's interesting to me that IBM has quite a few of these. The first measures of software defect severities, the first process assessment, the first design and code inspections. They didn't do all of these things, but they did quite a number of them. And all of them have been beneficial over the years. This shows the innovations from 1975 through 1985. And at the end of that time, you have the Software Engineering Institute coming in with their capability maturity model. So that was another significant event that occurred in the end of the 80s. We also have object-oriented programming, complexity analysis tools, and many other things that occurred during this decade. Switching between 1986 and 2001, we have yet another group of interesting innovations, and the one that I think in some ways is perhaps the most exciting, because we're sort of doing that today, was the last one, which is the launch of wiki-based collaboration. As you probably know, Wikipedia is now the world's largest and most widely used encyclopedia, and it probably never occurred to anybody that a collaborative effort involving thousands of people who've never even met could put together really useful kinds of documents and information. And so the entire web and the Wikipedia concept is adding greatly to the ability to communicate and to communicate very rapidly and share ideas. In fact, what we're doing today is one of the innovations that didn't exist only a few years ago, and I find it very helpful. Now, once you get one more thing about innovations, finish up to 2010. By the way, my phone is ringing, but I'm not going to be dealing with it. I'll just let it ring. Automated static analysis tools, virtualization, automated function points for legacy software, data mining, pattern matching. Yet again, another interesting set of innovations. The one in 2009 with MITRE, and also the SANS Institute, they developed an analysis of the most common software coding problems. And this will probably be significant to CMAT, and hopefully you already are linked up with SANS and MITRE and are planning CMAT to avoid the common problems that they quantified. They started with 25 common problems and then doubled the list to 50. Here are the approximate calendar times for development methods. Waterfall development, structured development, object-oriented, RAD, iterative, rational, agile, team software process, and then hopefully in the future, assembling applications using certified reusable components. As long as you are attempting to build something complicated using custom design and hand coding, it can't help but be expensive and error-prone. So the only way to really achieve true performance, close to zero defect quality levels, and very high productivity is to stop doing things by hand and begin to assemble them using standard reusable components. This, in fact, is what makes manufactured automobiles like Fords and Volvos inexpensive, and why race cars like Formula One cars continue to cost $1 million, is because they're built by hand to custom designs, and ordinary automobiles are built from standard reusable components. So what I'm suggesting for software is that instead of building software applications like Formula One race cars, where everything is put together by hand, we need to build them like Chevrolets and Volvos from standard parts. Now, I want to spend a few minutes on this slide because this one is a source of a lot of problems for the industry. This is the catalog of when problems were first discovered. When applications started getting big in the 1960s, it was discovered that as applications got bigger, requirements got less and less complete. And for big systems, sometimes they're less than 50% complete. And what that leads to is the next one. The measured rate at which requirements change during the development cycle is about 2% per calendar month. And I know that because we measure the size of applications and function points at the end of requirements, then we measure them again when the application is delivered, and then we backwards calculate between the delivery size and the requirement size and calculate the rate of growth, and it turns out to be about 2% per calendar month. And that's a topic that CMAT is going to have to deal with. How do you minimize the rate of requirements change from more than 2% per calendar month down to either a fraction of 1%, or how do you encapsulate CMAT so that it can deal with these rapid changes? Another issue is the third one, that requirements defects resist testing. You all remember the famous Y2K bug. Well, nobody ever wrote test cases for that for many years because it started as a requirements problem. And it wasn't until about 1995, until about 1995 that it was discovered that the Y2K problem was a real bug. Well, by the way, I just got some bad news. They're only able to record the slides because I hung up the phone and we're speaking on Skype, so you'll be able to see the slides but not my voice. So at this point, the only thing I can do is say I didn't think about that aspect of it when I hung up the other phone. So you won't be able to hear my voice. But in any case, those of you who have seen the slides can probably survive with that. The next one is testing is less than 60% efficient in finding bugs. Most forms of testing, like unit tests, only find about 1 bug out of 3, or only about 30% efficient. And even the best, like systems tests and integration tests, are only about 60% efficient. And that's one of the reasons why we need to do things before testing starts. We need static analysis before testing starts. We need formal inspection before testing starts, because the goal for quality is to achieve a cumulative efficiency of removing defects of more than 99%. And right now, the U.S. average is only about 85% defect removal efficiency, and even fairly good projects seldom get over 96 or 97%. But my goal, and I hope a goal for CMAT, is that every single project remove more than 99% of the bugs before delivery. And you can't do that with testing by itself. You need to include pre-test inspections, pre-test static analysis, and also defect prevention, such as quality function deployment, to reduce the number of bugs that you have to remove. Another problem discovered in 1979 is the fact that bad fixes are found in about 7% of all defect repairs. And what a bad fix is, it's a bug in an attempt to fix an older bug. About 7% of your attempts to fix a bug has a new bug in the fix itself. I once worked as an expert witness in a lawsuit where a company had 4 consecutive attempts to fix a bug in a financial application over a 9-month period. Each fix failed, each fix added new bugs. And finally, the 5th one after 9 months got it right. But this was a financial application, and the plaintiff in the suit was a company who had to restate its prior year's earnings because of this bug, and as a result, lost their good relationship with their bank, so their interest rates went up. So it cost them millions of dollars, not because of anything they did wrong, but because of a bug in a financial package that could not be repaired by the vendor for 9 months with 4 attempts to fix it. The next one, about 5% of modules contain 50% of defects. This was also discovered in the 70s in IBM, where they did a distribution analysis of bugs in the operating system and then the big IMS database, and found, to their initial surprise, that bugs were not randomly distributed. In the case of the IMS product, about 57% of all bugs were found in 31 modules out of 425, and there were 300 modules that had no bugs at all. So it was very interesting that there was such an unequal distribution, and this kind of skew has been found by many other companies. And so one of the issues for CMAT is how do you eliminate error-prone modules or very buggy components in large applications. 1980, about 35% of large projects were canceled. In 1980, again, most estimates are excessively optimistic. They generate shorter schedules and lower costs than really occur, partly because product measurements aren't very good either. The average in this country for measuring effort is only about 37%. In other words, only about 37% of the true costs are really measured. The most common things that are left out are project management, unpaid overtime, and the work of many part-time specialists such as quality assurance, technical writers, database analysts, and the dozens of people that come and go but are not full-time employed on a project. And finally, the last point, only 85% is the average for defect removal efficiency before delivery in the United States. And it's the same in Sweden and Norway and most other countries. Now, what are the benefits of excellence? How do you judge when you have excellence? How much can productivity be improved? How much can maintenance productivity be improved? These are the topics that are probably important to CMAT as well as important to the industry as a whole. What will be the ultimate benefits or the ultimate goals from CMAT, and what are the things you need to do to achieve those goals? Well, the benefits are better customer satisfaction, better staff morale, reduced risk of project failures, early risk abatement, improved status with top executives. And the risks, because sometimes project improvements don't work, are spending more than necessary to achieve positive results, selecting methods that don't work for all projects, like jumping blindly into Agile when you should be using team software process, expecting excellence in just 1 year, abandoning success after it's been achieved. I revisited some of my clients from 10 or 15 years ago and found that about 40% of companies drop successful methods after 5 years. And this is going to be very important to CMAT because you don't want people that successfully use.
After that nice chorus of uh-oh.
Now we can go through the slides.
From the one started the process improvements, didn't understand the value of the process improvements, and brought in methods that weren't as good as the ones that were there when they arrived. So what you have to do to ensure that this is going to stay current is to have very good measurements that are passed on to the people who come in to replace those who are promoted, and also good training programs to be sure that the technical workers and managers understand the value of the improvements of things like CMAT when they first come aboard. So you need entry-level training for everybody and continuous measurements for everything you do to demonstrate that what you've done has been a success case. Now,
excuse me, Capers?
Yes.
We lost your video there.
You're not seeing my screens anymore?
We hear your voice, but we don't see your video. Maybe it's just in the Skype. I had to press the video button on my Skype. We lost you for a second, and then when we returned, it seemed that we got a voice conversation instead of a video.
Okay, I'm going to call into Avery.
No, you don't.
Take copies.
I think all you have to do is press the video button on Skype.
Oh.
I hope.
Are you sure? Because we're not using Skype for video. When you mean my face, you know
yeah, your face is gone.
No? Hold on. I have to minimize the screen in order to get to Skype.
You don't need video.
Just a second.
Okay, let's just see if... Yeah, so you see you have a crossed over video camera in your screen there. In the picture, if you move your mouse to the picture, to where Eva is sitting, then at the bottom there you see you get a menu, and there is a video camera with a red there.
Turn it on again.
There, that's it.
Excellent.
Okay, thanks.
I wonder how that turned on.
Well, we got disconnected from it, then we were reconnected with a voice call.
Okay.
To see your slides.
Are we back now with the?
Yes.
Yes. Everything is good now.
Okay. All right. Benefits, better customer satisfaction, risk I've already discussed. Now, here's what it means to be excellent in software engineering. I like to quantify things, so these are quantified numbers that you can use. You should have no software project cancellations due to major cost or schedule overruns. That should be 0. The maximum that a project should overrun its budget is 5%. The maximum that it should overrun its schedule is 3%. And
Time out.
Does it? It never happened to me.
It's connecting again.
Just leave it as voice this time.
Yeah.
Just let him talk.
We don't need to see me.
I understand.
I mean, it's enough with the slides.
Can you hear me?
Yes.
Okay, I lost the picture of you now, but if you can see me, I'll continue.
Yeah.
Yeah.
And we can
Okay.
leave the room.
In any case, all right, you're back again. Software, high productivity, significant reuse, more than 75% of everything. Design, requirements, and test cases reused and all certified. Development cost of less than $500 per function point. The US average is about 1,000. And I imagine in Sweden it's probably slightly higher because the, probably around $1,100. Development schedule should be 25% shorter than industry average. Now, these next two are very important. The current average is about 5 bugs per function point when you add up requirements bugs, design bugs, coding bugs, user document bugs, and bad fixes. And the goal is to get down below 2.5 bugs per function point. And the goal is to average more than 96% defect removal efficiency. Now, every company should measure defect removal efficiency because it's easy to do. If I deliver software to Pontus, let's assume that I do, and I found 90 bugs, and then he runs my software and reports 10 bugs in the first 3 months. After 3 months, I add my customer bugs with my bugs. I found 90, Pontus reported 10, so I'm 90% efficient. That's an easy metric, everybody should do it. And if you are not in the high 90s in your defect removal efficiency, you obviously have something wrong with your development process. Probably you're not using inspections or static analysis, you're just depending on testing, where you'll never get into the 90s for defect removal efficiency. So you also need low levels of delivered defects, and the next one, number 11, is important too. How much software can one person, one maintenance programmer, keep running in the course of a year? The US average is about 1,500 function points, but a really good, well-structured application, hopefully one developed under the CMAT principles, one maintenance programmer can handle over 3,500 function points. In fact, for CMAT, I put it even bigger. I'd say a target for CMAT is that one maintenance programmer should be able to handle 5,000 function points, or more than 3 times the average in the United States. So the maintenance cost should be below $75 per function point, and then some subjective goals. Best customer service, best user satisfaction, highest team morale, and best compensation and benefits. Now, how do you get there? How do you do all these things to become really good? First, you have to start with an assessment and baseline, which is like going to a medical doctor for a diagnosis, for your annual physical checkup. The assessment does not cure any problems, but it will tell you if you have any problems that need to be cured. And then if you have problems that need to be cured, the doctor will write a prescription for the things that you have to do to get better. So you start with an assessment and a baseline. The assessment is the analysis of the methods that you use, and the baseline is a quantification of your productivity in function points, your defect removal efficiency. It's the numbers that describe where you are today. And then once you have done that, you need to set goals. Do you want to be the best in class, better than average, or better than you are today? And in order to do that, to be best in class or better than average, you stop doing the things that the diagnostic study has told you were wrong, and you do more of the things that have been proven to be right. In other words, you start doing static analysis, you start doing inspections, you don't depend purely on testing, and then you develop a 3-year technology plan, which CMAT is already envisioning, but it needs more than just software engineering. It also needs to include things like capital equipment, new tools, office space, education, how much are you going to spend each year on training, culture, programming languages, and return on investment, because top executives are going to want to know what kind of yield they're going to get for every dollar that they spend on improvement. So you have to demonstrate the value of what's going to happen when you can end up building software with better quality and in shorter schedules. Now, since I have data on around 13,000 projects, here are the main reasons for failure and the main reasons for success. On the failure side, no automated sizing tools, no estimation tools, no planning tools, no progress reporting. By the way, in all the lawsuits where I've worked as an expert witness, progress reporting has been a very weak link. It looks to me like project managers almost deliberately conceal problems until it's too late to fix them. You'll see something like that later in this talk. Inaccurate cost collection, no measurement data, inaccurate metrics, no reviews, no inspections, no defect trackings, informal change control, and unstable requirements with more than 30% total change. On the right column, where things go well, you obviously have the opposite of everything in the left column, ending with the bottom one that you have less than 10% total requirements changed during the development cycle. Now, there are also social reasons as well as technical reasons. And for the unsuccessful projects, here are the social problems that show up. Excessive schedule pressure, severe friction with clients, poor communications, divisive politics. I've seen projects canceled where managers on the same team did not like each other and refused to cooperate. Naive senior executives, management malpractice. And management malpractice means deliberately concealing problems from clients or top management rather than being proactive in trying to solve them. Technical malpractice, which doesn't occur very often, but the next one occurs far too often, untrained generalists. In every field, medicine, law, software, trained specialists are more efficient and more effective than untrained generalists. And the major topics where you need trained specialists to do a good job are quality assurance, testing, and planning and estimating. Ordinary developers are much less efficient than trained certified testing specialists in finding and removing bugs. For example, if you look at the results of new function testing by the developers, that's only about 25 to 30% efficient, find less than 1 bug out of 3. But certified test personnel who use mathematically based test case design based on things like design and experiments are like 45 to 50% efficient in finding bugs for the same testing. So there's a significant advantage in using trained certified test personnel as opposed to untrained generalists. And finally, on planning and estimating, which is a field I work in, ordinary project managers don't have enough historical data in order to be really good at estimating. And the normal things that amateurs do, like project managers in estimating, is that they're okay in predicting the coding costs, but they way understate the number of bugs that have to be removed. They way understate the cost of producing paper documents, like requirements and design, and they way underestimate the cost and schedule of testing. Most projects that are late are on time until testing starts, and they run late because they have so many bugs in them that testing stretches out to 2 or 3 times the planned allocation of testing time. So too many bugs when testing starts is the main reason for schedule delays. And you can see the opposite case is doing the things better that were done poorly in the unsuccessful project. But there are also some intermittent factors that only occur every now and then. Geographic separation, like suppose you have developers in India and Sweden. If you don't have good communication, you'll have problems. Same with multiple subcontractors. Projects that are bid using only low bid as sole contract criterion instead of including quality in the contracts, only including cost, that's never successful. Quality has to be in the contract as well as cost. Staffing buildup, more than 15% per month if you have to hire people too fast. Or staff attrition of more than 40% of the project team. I worked in a company once where 65% of the IT staff quit in the same week because they were dissatisfied with the personnel decision. A popular CIO had been replaced with someone who was known to be incompetent, and so 65% of the staff quit. So if you lose that many people, you can't hope to keep your projects on time. Abrupt introduction of new technologies, like dumping Agile into a team and expecting them to be immediately successful on the first project in the first week. Projects by companies that are downsizing, new executives try to replace proven methods with the latest fads, and finally trained personnel who retire or change jobs and their replacements aren't very confident. Now, this is important, and it's going to be important with CMAT too. If you look at the qualities and the performance of project managers, technical personnel, and software users, you discover that in the United States at least, the technical workers, the people handling requirements, design, coding, reviews, and testing, generally are fair to good. The real weakness in software project management, where most managers are poor at estimating, tracking, and measuring, and we also have problems with clients or users because they're very poor in expressing their own requirements and extremely poor in demanding schedules that are technically impossible, that nobody can achieve. So we definitely have to look at the ends of this spectrum rather than the technical staff as the main source of problems. Now, worst case scenario, if you have ineffective technologies, inadequate tool suites, and less than 5% component reuse and poor project management, You can expect canceled projects at 15%, 75% delays, on time only 10%, and never early. I'm not going to go at length to these others, but this is what you want, and this is what you want CMAT to have. 75% on time, 12% early, and any delays, the 12% there, will be caused by external factors and not by poor quality or internal project problems with the project itself. Now, this is one of the main problems of the entire industry. If you look at the actual schedule, you can approximate that by taking function points and raising it to the 0.4 power. But if you look at the scheduled demands by clients, what they want, you need to use the 0.3 power. So a endemic problem, a chronic problem of the industry is that clients always want things faster than we're actually able to build them. So the task is either to be able to build them faster, get to the 0.3 power, or convince clients that it can't be done at the 0.3 power and give them realistic estimates that they can live with. So this is a major issue for the software industries. Now, software paperwork. Finding and fixing bugs is the most expensive thing in software. The second most expensive thing is paperwork. Some military projects put out more than 400 words per line of code or 4,000 words per function point. Many more, and they cost more for the words than you can spend for the code itself. So you definitely have to include paperwork cost reduction in any significant attempt to improve productivity or schedules. This is the risk of project failure. Small projects below, say, 500 function points are usually successful. Big projects above 10,000 function points canceled or delayed almost all the time. So one of the things CMAT has to do is to be able to scale up to really big systems bigger than 10,000 function points. And also the higher CMMI levels have reduced failures compared to the lower CMMI levels. Now, this is the risk of delay and the risk of termination based on CMMI level. So the high level CMMI 4 and 5 have much fewer incidences of delays and much fewer odds of termination than the lower CMMI levels. Now, software life expectancy. This is something CMAT should pay attention to also. How many years are you going to keep the software that you deliver running? It turns out that some software projects run for 25 or 30 years, and hardly anybody plans for that. There may not even be any compilers available after 10 years, so long-range planning is something that CMAT has to be cognizant of. After software is delivered to customers, it doesn't stay static. It continues to grow at a rate of 7% per calendar year forever, as long as people are using it. So you also need to deal not only with the initial release, but with continuous releases for 10 or 20 years downstream as new features are added every year. This is productivity rate for new projects. Very high for small projects, very low for big projects, as you might expect. But when you switch to maintenance, you end up with a different curve. What happens is that the productivity peaks for maintenance when the size of the change is about 3% of the size of the application. Now, when you make bigger changes, you have structural changes that degrade productivity. But why do you have low productivities for small changes? It turns out that that's due to the overhead of testing and getting rid of bugs, because every change you make to a big system risks the damage to the big system itself. So you have to do a lot of expensive regression testing, and that makes small changes extremely inefficient and expensive. This is what the overall picture looks like, with mid-sized projects being the most productive, more productive than massive new projects or small enhancements. Now, quality. This is a chart everybody can use. The US average is somewhere between 4 and 6 bugs per function point, and up to about 85% defect removal efficiency. Where you want to be is down in the best in class end of the zone, not up in the malpractice thing. And to do that, you need to get below 2.5 bugs per function point and up above 95% in defect removal efficiency. And everybody should measure defect removal efficiency because that's a powerful metric. Now, there are 7 stages of software excellence. I'm not going to go through them quickly. Just going to tell you how long it takes. This is up to 60 months for a big project with over 1,000 people or a big company. 2 years for a small or enterprise with only 10 people. Expect up to 5 years if you're dealing with big industries with over 1,000 people in their software team. This is the benefits from each phase. And you'll notice that you get the best results when you hit stage 5 on reusability. That's where you really pick up on software defect reduction, software productivity, and schedule compression. And you can't skip phases and try to do reusability first, because unless your quality is state of the art, reusability will backfire and make things worse instead of better. So the ultimate goal is to have a 90% reduction in defects, a productivity increase of 250%, and 70% compression in schedule. So CMAT should probably do that in the fullness of time. Now, this is what it costs to achieve these things. It isn't cheap. If you work in a big organization with up to over 1,000 people, you can expend over $20,000 per person over about a 5-year period to achieve all these things. Another interesting fact, when you do your first assessment, how fast you can improve is based on how bad you are when you start. Imagine what it's like to, say, train for an Olympic event, like a race. If you're 50 pounds overweight, you may never be able to run an Olympic race. But if you already work out, if you're in good shape, you can only train for an Olympic event in, say, 6 months to a year. So where you are when you start determines how fast you can progress. Now, the best case for process improvement is about a $20 return on every dollar that you spend. This assumes 2 years of improvements and 3 years of results. And the main value that you'll get is the value from better quality. The second main value is from shorter schedules. However, not every process improvement program works. The worst case I've seen, you spend $1 million, but you only get 50 cents back on every dollar because you didn't do it right and you botched up some of the improvements. You either made your team mad or you selected methods that didn't work. You did things that were ineffective, is the bottom line. Now, these are the things that are important to each of the stages. I'm just going to go through them. I'm not going to talk much about them because we're running out of time. The final point, the best companies that I've worked with quite a few, IBM and Microsoft and Motorola, things like that, these are the things that make them good. Good project management, good technical staffs, good support staffs, good measurements, good organization structures, good methodologies, good tool suites, and good environments. And CMAT needs to really encompass every one of these things, because if you just deal with methodologies on 6, that isn't sufficient. You need to encompass the entire set of the 8 factors on this page. We've now run to 30 minutes, and I think it's probably best to stop and see if there are any questions. You can read the rest of these things, which just list what goes on in each of the phases.
Okay, thanks a lot, Capers. Maybe you could see if you can turn on the video again, because we lost you there. Just press the same button again.
Oh, I'm sorry about that. This has certainly been an unreliable experience with Skype today.
Yeah, well, it could have been worse. Okay, so
Wait a second, I haven't gotten. Something's happened to my cursor. It's invisible to me right now. Just a second.
We can see it though.
Here we go. Okay, are we back?
Yes, you're back.
Okay.
So questions, anyone? Well, I have a question, Capers, and that is regarding you do a lot of predictions and you have a lot of recommendations here, and this is based to a large extent on data. You talked about that you have 30,000 projects. Can you tell us a bit more about that?
13,000. 13?
Okay. Can you tell us a bit more about that?
Well, I'll count to 13,000 from one and tell you, no, I can't do that. For the most part, I started this work in IBM, so I had total access to IBM's internal data. Then I moved to ITT, and I had total access to ITT's data, about 7,000 projects between those two. And then when I started my own company in 1984, every month we had people going out on site, sitting down face-to-face with development teams, and asking them a detailed set of questions about the methods they were using, the tools that they were using, and then measuring their productivity and quality. So we were getting data from 25 to 75 projects per month for more than 10 years, and then collecting that, and then showing the clients statistically what were the things that worked best and what were the things that they wanted to avoid. But we got that data by actually sitting down face-to-face with those teams and measuring what was going on. So that's where the data comes from. It's all primary data. I don't use secondary sources. This is data that I had personal access to.
Do you know of anyone who has this amount of data about software projects?
Yes, I do. I have a catalog of software benchmark sources that lists 21 companies besides my own that produce software benchmark data. For example, the International Software Benchmark Standards Group in Australia has over 5,000 projects, and you can acquire their data commercially. Because the data is normally gathered by companies that build estimating tools, like my own former company and my current company, all of the estimating companies like Price Systems and Galler and QSM, tier estimating tool, usually have from 10 to 20,000 projects themselves.
Okay. Let's see. Capers returns. Well, are you back, Capers?
I'm here.
Yes, we lost you for a second there.
Can you see me again?
Yes.
Could you hear my voice that I can send you the catalog and you can distribute it because it isn't copyrighted?
Sure.
Okay.
Okay, so
Any more questions?
no more questions.
Sorry, what is the size of these projects roughly? What a range of the sizes?
I couldn't hear the question.
The question is, what's the range of sizes of the projects that you have data on?
Well, that's a very good question. The size ranges from a low of about 100 function points to a high of 300,000 function points. Let me tell you some of the bigger projects because you probably don't have access to data from them. The Worldwide Military Command and Control System is about 300,000 function points. Big ERP packages like SAP and Oracle are about 250,000 function points. IBM operating systems like Windows 7 and Windows 8 are about 160,000 function points. So those are the bigger projects in my with data. I normally am only commissioned to work on fairly large projects by fairly large companies, so I have a shortage of data for little projects that are, say, 100 to 200 function points because nobody bothers to measure them or to study them very much, primarily because they don't get in any trouble. The big systems are the ones that get into trouble.
Thank you.
Thank you, Capers. Any other questions? Okay, well, thanks a lot, Capers. Thank you.
Thank you very much for